Hey, it looks like we're going to solve some right triangles. A couple neat tricks that are available when it is a right triangle, right? When we just have a regular old scalene triangle or obtuse triangle or acute triangle, it gets a little trickier. But with a right triangle, well, for one, we can use the Pythagorean theorem. And then, of course, we also have SOHCAHTOA, right? Sine, cosine, tangent. We can use those trig ratios to unlock some more information. We saw some of these basics back on PowerPoint 5.1 and PowerPoint 5.2. Those are available on Quick Schools. And then these skills are pretty heavily embedded in all those IXLs I said that you might want to take a look at over winter break. Now again, for each one of these, it is a right triangle. Right? If we don't have a right triangle, then we need some other tools. Of course, very helpful to have a picture. Of course, we're not all super duper artists, so maybe just draw a simple triangle, remembering that it's got to have a right angle. Right? One of the angles needs to be 90 degrees. And then also as a reminder, we also use capital letters for the angles. Since I know A is supposed to be 36 degrees, I'll add that to my diagram. Since I know side B is 8.2, I'll add that to my diagram. Notice the 8.2 for side B is across from angle B. Well, if I have two angles, I obviously know the third, because those angles have to add up to 180 degrees. So it's real quick to get the third angle if I know two of them. I can add that to my diagram, and I can add that to the list of the 6 parts. Right? Start out with 3 pieces. I now know 4 of them. So I choose an angle. I decided, hey, I'll take a look at this 36-degree angle. Once I choose an angle, I know what side is opposite. I know what side is adjacent. And of course, the hypotenuse was predetermined. It has to be across from C. So if I want to find the measurement of the opposite side, and I know the adjacent side, SOHCAHTOA tells me I have to use tangent. Tangent of theta is the ratio of the opposite side to the adjacent side. Or in this case, the tangent of 36 degrees has to be A over 8.2. Right? The side opposite angle A is lowercase a. I can grab a calculator, figure out what is 8.2 times the tangent of 36 degrees. Make sure my calculator is set for degrees, of course. The directions on the slide do not indicate where I should round off, and so I will just round off to the nearest tenth. I can add that to my picture. I can add that to my list of pieces. So I now have 5 of the 6 pieces of the triangle known. And since I know 2 of the sides of a right triangle, I know both legs. I can grab the Pythagorean theorem. Notice I don't use 6 for A. Right? I rounded off the answer to the nearest tenth, so I put 6.0. But I can actually use the answer in the calculator's memory. Right? I can just request, hey, take the previous answer, square it, add the quantity 8.2 squared, take the square root of that whole thing, and then round off afterward. Usually doesn't make a huge difference, but you don't want to use information that's overly rounded off to then go pursue and find new information. Of course, I can add that 10.1 to my diagram, and I can add that 10.1 to my answer display. I now know all 6 pieces of that right triangle. Slightly different example. Before, I was told I was told 2 of the 3 angles. This time I'm only told 1 of them. Again, I want a picture. 3 is side A. 7 is side C, also known as the hypotenuse. Well, pick a corner. I'm going to pick angle A again. So I now know that 3 is opposite. Side B, which I don't know, is adjacent. Hypotenuse is 7. Now, of course, if I'm going to work with opposite and hypotenuse, I've got to use sine. Right? SOHCAHTOA. S-O-H. Sine is opposite over hypotenuse. So sine of angle A has to be 3/7. So I actually need the arc that creates the sine of 3/7. That will tell me the angle. Again, make sure I'm in calculators on the degrees. Notice when we're solving right triangles, we normally use degrees. When we use the unit circle, we normally use radians. If I've got the answer, I can add it to my diagram, and I can add it to my answer display. Hey, I now know 2 of the angles. I know the sum has to be 180. Notice I didn't worry about using the rounded off value of 25.4 here, because I want the 3 angles to add up to 180 degrees. Pythagorean theorem. Uh-oh, it's one of the legs I'm missing. So instead of adding the quantities of a squared and b squared together, we're going to actually have to do some subtraction. So b squared equals 40. Now, when we're solving with the unit circle, we normally want exact answers. And so we would then simplify it to be 2√10. But when solving right triangles, it's customary that we actually find a decimal approximation. And so I'll use 6.3. So a couple odd things. When we solve trigonometric equations, answers are usually given in radians because we're usually working out the unit circle. But if we're solving right triangles, it's quite customary that the answers are actually given in degrees. When we're solving trigonometric equations, the answers, as much as possible, should be exact. But when we're working with right triangles, answers are often rounded. Kind of a little bit of a peculiarity. But again, always check the directions, because sometimes the directions will actually request radians, or the questions might request degrees, or the directions might request exact or rounded. And it looks like we're being visited by a dragon this time. And a pterodactyl.